My name is Sunny, and thank you for tuning into my video about the master's thesis topic that I'm exploring, which is evaluating the strength of the subgrade that we need to have in order to pass a proof roll test. Let's get started. So why am I doing this master's thesis? The purpose is because generally during road construction, once we strip out to subgrade level, once the topsoil has been excavated, generally a proof roll test is done to determine whether the material is suitable for subsequent construction to take place. Generally, the proof roll test is a pretty good test to determine where the soft areas are, but the proof roll test generally needs the subgrade to be a certain strength so it doesn't deform. And we just want to understand whether that strength requirement is necessary. It's one thing to determine a soft spot, it's another thing to determine whether a subgrade has to be a certain strength in order for subsequent construction to take place. So, what is that strength that you need in terms of the undrained shear strength of the clay? What is that strength? And does it actually need to be that strength? Or can it be weaker? Can it actually fail a proof roll test and still be okay for construction? We're probably not going to go that far, but it is important to understand, maybe what is that undrained shear strength that the clay needs to be so that the subsequent construction can take place, that the proof roll test doesn't deform. And I do agree that it's a useful test, but let's explore this topic further and keep going. So why are we doing it? Again, are we doing it because we need a stable platform for subsequent construction, or whether we need to prove that the subgrade meets the design CBR intent? It's a good question. Let's keep going. So one of the things that the paper will look at is undrained shear strength versus in situ CBR, and then how do we test for that in situ CBR strength. So this is a table that was prepared by Das, and it defines the various clay strengths and parameters, the measured shear strength using vein shear testing, DCV blows, what that roughly correlates to, and then the correlated in situ CBR, which has been calculated from the Ostroids methodology, so which is penetration per blow. So we can see roughly that say a shear strength of about undrained shear strength of about 20 kPa, soft clay roughly 1 blow per 100 mil, and an in situ CBR of about 1 to 2, roughly about 1.5 to 2. So this paper will look at say we've designed a subgrade, we've designed a pavement for a CBR of 4%, which would be a fairly high CBR for a high plasticity clay, 4%, but say we've designed it for 4%. Do we actually need the subgrade to pass the proof roll test? The pavement's been designed for 4%. In other words, the pavement strength or the pavement thickness above it can sustain a pavement which might actually fail a proof roll test, but the proof roll in this case is being done more for subsequent construction to take place, not necessarily because the pavement can't handle that strength. So let's keep going. So the origins of the proof roll test. The term proof rolling was first introduced in the United States mainly for crushed rock, actually, not even for subgrade. It was introduced for crushed rock in 1957 by Turnbull and Foster, and it was actually a way of checking that the crushed rock base course was meeting the design intent. And the proof roll equipment was actually quite different to the one we use in Australia. Here in Australia we use water trucks, or we use smooth drum rollers. They actually use quite heavy rubber tired rollers. I've got a photo later on in the PowerPoint about the equipment they do actually use, but it's quite different. And as you can see, Turnbull and Foster defined the proof roll as a procedure to check the adequacy of the normal compaction and any deficiencies that may exist. So it was actually used quite heavy equipment, much higher up in the construction sequence, and it was more to identify soft spots. You know, you knew what the strength of the material was. It was really about identifying soft spots. So have we lost some of that purpose of the proof roll test? You know, it was about identifying soft spots, not actually determining the strength of the material itself. So, you know, it was a very qualitative test, I guess you could say, not a very quantitative test. And are we still using it for that purpose now? Yeah. So now, specifically for our master's thesis, we're focusing on VicRoads section 173, or how, you know, what strength the subgrade has to be in order to meet the requirements of VicRoads section 173. And just, you know, I won't read it all out, but essentially you can, you know, do the test using either a 20-ton water truck or a 12-ton static smooth roller, and it defines certain minimum tire pressures and contact areas. And most importantly, compliance is when the area can withstand the test rolling without visible deformation or springing. Visible deformation or springing. What is visible deformation or springing is a good question, I guess. And do most 20-ton water trucks, 12-ton smooth rollers, what sort of contact area do they actually have? And what sort of tire pressure do they have? You know, is it around the 450 kPa, or, you know, the 0.035 square meters per tire, the contact area? Like, what is the contact area? What is the tire pressure? And, you know, what is visible deformation? Good questions. Let's keep going. So, just, you know, in general, most, or in Circly, we model, you know, the pavement, and it's generally modeled at about 700, 750 kPa, a standard axle tire pressure. So we can see that, you know, in general, we think that most tire pressures are around 700. You know, it's a fairly safe assumption to make, but, you know, 700 to 800, some are getting up to 850 kPa, very heavily loaded vehicles. And, you know, a single steer axle, single tire, 6 tons, single axle, dual tire, 9 tons, tandem axle, dual tire, 16.5 tons. You divide that by the number of tires, 2, 4, 8, and you get the equivalent weight per tire. Roughly, if you look at that, it correlates to about 700 kPa tire pressure and about 2 to 2.5 tons per tire, the equivalent load. So the tire pressure is higher. 700 is higher than 450, and, you know, the contact area we're assuming is what VicRoads says it is. And, you know, that's another question. You know, is that accurate? Is that contact area accurate? And, you know, which tire should you be looking at? The front axle, the rear axle? You know, where should a proof roll test actually be observed? The front or the rear? So if we were to follow VicRoads methodology in terms of the actual tire load, it should actually be the front axle, not the rear axle. But, you know, most people do it on the rear axle. So this is just a, you know, sheet going through all the various combinations and what the maximum mass limit is in tons of each of the axle configurations. So we can see anything from 6 all the way up to 16.5 tons there, depending on which sort of configuration we have. So, like I said, you know, if we were to actually look at what VicRoads says in terms of maximum mass on the tire, we should actually be observing it on the front axle, because, you know, that's where the 2.5 tons actually occurs. But we mostly always check at the rear axle. Now, this photo in particular doesn't actually have the type of equipment that VicRoads section 173 says. I couldn't quite find a photograph that had that, but this is actually the typical methodology. You have two people walking, observing the rear axle of a 20-ton water truck, or a smooth drum, or actually a 20-ton water truck, or some sort of a heavy truck equivalent to about 20 tons. And they usually only observe the rear axle. Not many people observe the front axle. And, you know, is that even the right way to do the proof roll test? So, you know, maybe it's a, you know, lack of understanding of, you know, the weights, the pressures, the contact area, a bunch of things, you know, about why the proof roll test is actually being done in the first place. So what is, but you know, those are all some things. That's, you know, the contact area, the stress, the tire pressure, where it's being observed. But another limitation is the speed of the vehicle. The Vic Roads doesn't actually define a speed for the proof roll test to be undertaken. I guess you can't do it too fast. You should be able to walk alongside it and observe it. But does speed make a difference? Obviously, you know, the longer you load an area, the more it will likely deform. So speed does make a difference, but you know, is there a speed that you should be observing it at? In 1996, there's a paper by Brown and also the paper by David Mangan that I'm continuing on from. They both concluded, and even Smith in his paper, Colin Brander and Smith in their paper concluded that speed is a very important factor for the proof roll test. And it should generally be, you know, between 3 to 6 or 4 to 5 kilometers per hour for a proof roll test, because you should be able to walk next to it, but it shouldn't be too fast, but it shouldn't be too slow either. So, you know, there is a pace that the proof roll test needs to be done at, and that pace is important. So, you know, like we said, one of the compliance methodologies or criteria for Vic Roads Section 173, by the way, we're using Vic Roads because we are in Victoria. This is my, you know, area of, you know, application, I guess you could say, where I'm working, where I really want to know, you know, how is it being applied and what are the consequences. And in Victoria, Vic Roads Section 173 is applied for the proof roll test on state roads. And the governing criteria is no visible or no perceptible deflection or deformation. Now that we've gone through how the proof roll test is done, let's look at the evaluation criteria and what actually is visible deformation. So we've concluded that, you know, the proof roll test isn't actually being done specifically to Vic Roads criteria, because we're observing the rear axle when we should be observing the front axle. We're exerting much higher tire pressures. Sometimes different equipment is being used. The tire configuration is different. Like there's, you know, the methodology is really being applied the way this section has been written. So the methodology has been applied differently. It's understood very poorly. There's no speed criteria actually being applied to it at all. Now let's look at if the deflection, the assessment criteria is being applied to it, the evaluation criteria, the way it's been assessed. So what is visible deflection or deformation? So back in the 1960s, the Commonwealth Department of Works, they looked at, you know, a procedure to evaluate the strength of the airfield pavements. So a lot of this proof roll testing actually started from airfield pavements back in the 50s and 60s, as we can see, and it's now made its way to every road project everywhere in Australia and maybe globally. So they looked at, you know, how should a proof roll test be done, speed, deformation, deflection, all that sort of criteria, and Brown concluded that, you know, the speed should be 4 to 6 k's an hour, 2 people walking beside the roller and observing the deflections. And they looked at, you know, classifying deflections in many different ways: visible deflection, barely visible, clearly visible, marked deflection, and marked deflection accompanied by permanent deformation. So they had, you know, A minus A plus B, C. So they, you know, they rated the deflections they defined the deflections, and then they said, okay, what does what does it need to be to pass from our point of view, and then what does that pass look like quantitatively, and what is visually being observed like? So they concluded that a standing observer would not be able to observe anything smaller than a B, marked deflection without any apparent deformation, which is between 1.1 to 1.9 millimeters, or on average 1.5 millimeters. So we actually can't observe from, say, a few meters away anything less than 1.5 millimeters, they concluded. You know, that's visible deformation, 1.5 millimeters from a few meters away. And I'm not saying 10 meters away, maybe I'm saying, you know, the same distance, maybe 1 to 2 meters away. It's actually very difficult to see anything smaller than 1.5 millimeters. You wouldn't observe it, you wouldn't notice it. So the limit of visible deformation from, say, 1 to 2 meters away is about 1.5 millimeters. They also show that the distance should be, or the distance of 1.5 millimeters should be, you know, apparently 300 millimeters away from the tire. 300 millimeters, you know, is that longitudinally, transverse direction? They didn't quite define that, but what we'll see is like that 300 millimeters is actually, if it's in the longitudinal direction, it's quite different from when it's in the transverse direction. They're actually quite different things. They are a result of different loadings, and they actually are different in the way they behave. But they just said, 1.5 millimeters, 300 millimeters away, if for an observer about within 1 to 2 meters away. So that's what they said should be the assessment criteria. That's visible deflection, that's visible deformation. By the way, deflection and deformation are two different things. Deflection could be something that rebounds back. Deformation is something that stays. So just to be clear. That's another thing, Are we assessing deformation or deflection? Because they are different things, and which one is more important? So just now looking at, what proof roll testing methodology is being adopted around the country right now in Australia. So we have all the different state government bodies. We've also got the infrastructure design manual, which is used in Victoria for regional councils mainly. Sorry about all the coughing. So we've got Vic Road Section 173, the Australian Standard, which is quite similar to Vic Roads, the IDM, the Infrastructure Design Manual, which basically also adopts Vic Roads and the Australian Standard, RMS New South Wales, which is a bit different in terms of the wheel loading and the water truck, the weight of the water truck. Transport and Main Roads, which refers to the RMS in a way. South Australia, Department of Public Transport Infrastructure, Planning, Transport and Infrastructure, and Department of State Growth, Tasmania, which refers to Vic Roads. A lot of their standards refer to Vic Roads. So all the standards are there. This table was extrapolated from the David Mangan paper. Good summary. And you can see some of them talk about speed, some of them talk about pass. Actually, only one of them talks about passes. Most of them define the weight and the contact area. I guess there's no universal, methodology that's being applied other than the deformation criteria. The weights are slightly different. The passes, the speed is being defined in some cases. In other cases, it isn't. So, yeah. And how are they assessing it? Most of them are assessing it based on, it just should not have any visible deformation or rutting. So they're mostly all saying, the same thing, just no visible deformation or rutting. Coming back to the point about, 300 mil away, within 1.5 to 2 millimeters, you can see, when you impose that 300 mil rule, which way are you imposing it? 300 millimeters, deflection should be less than 2 millimeters, on a 300 millimeter, wave. Is that transverse or longitudinal? And it does make a difference. It makes a big difference. So, so that was all the theoretical stuff. What led to this thesis being carried out. Now, let's look at a case study. This was a project I was involved in maybe 3 or 4 years ago. A road construction project in Victoria here in 2019. My company, the company I work for, Tonkin & Taylor, we were engaged by a developer to look at some subgrade proof roll testing in the western suburbs of Melbourne. I went out there, I observed some proof roll testing. Very subjective test. Half the people on site thought it was good, a couple of people thought it wasn't. And so, we were like, okay, let's do some sort of quantitative testing. There's a difference of opinion here. Maybe it would help to, get some DCP testing done, some shear vein testing done to work out, what is the subgrade strength here? Because there's a difference of opinion based on the visual. Let's do some subgrade testing. Let's do some DCP testing. We did some DCP testing. We did about 25 DCP tests from memory, I think, every 20-25 meters. So they were quite frequent. Again, the proof roll test, the one good thing about the proof roll test is it's a continuous test and it identifies soft spots. We do need to do that. I'm not disagreeing on the good things about the proof roll test. But do we actually need it to be a certain strength is what I'm questioning. So again, we did the DCPs. As you can see from the DCP blows, the majority of it is actually, aside from DCP 13 there where we've got a 2 at the top, the majority of the DCP blows are 3 or greater. In fact, we're getting shallow refusal. So it's stiff to very stiff clay. There's 1, 2 there at number 13. Again, stiff to very stiff, hard clay in some instances. Number 23s, we've got a 2 there. So just looking at those DCP results, you'd say this is pretty stiff clay, stiff to very stiff clay. The in-situ CBR is about, 5 to 10 here. Easy. And yet, some people are saying the proof roll test is failing, and some people are saying it's passing. So it's, this is the thing about a subjective test, a visual test. It's, it's dependent on the observer to a certain extent. But when you do the quantitative testing, it's quite, definitive here. So the outcome in this instance was the proof roll test was considered to fail because visual observations didn't quite stand up, and they had to replace almost half a meter of subgrade. So, but coming back to the point that we were getting DCP blows between 3 and 5, leading to an in-situ CBR of 5 to 8. On the low end, not on the high end, on the low end, not even the average. The average was actually quite high. You can see that based on the paper from Colin, Brander, and Smith, they did some modeling in Circly to look at what the deflection of the subgrade would be based on the CBR strength of the subgrade. So if we had gotten those DCP values, correlated it to an in-situ CBR strength, which we did, done the modeling using, Circly 5 back in the day, you could, even now if you have Circly 5, you can do this. You can do repetition of a standard axle. You can do a single drop, place a load, work out what the deformation is. They did this. I think that's how they did it. I'm not exactly sure how they did it, but I can do it in Circly 5. I've done it in the past. And you can see what the deflection of the subgrade is. And you can see that, when the subgrade strength is between 4 and 8, the deflection is always less than 2 millimeters. So there shouldn't have been any visible deflection. But again, it's a subjective nature of the test, right? And I guess there is, there is always this, it's a continuous test. So maybe, the DCP tests were done 20 to 25 meters apart, and in between there were isolated areas of weakness, and I agree with that. There are always these cases. But, in this case, all 400 meters or 300 meters of that road was ripped out at half a meter. So, again, do we need to, is there a more quantitative way of, assessing subgrade strength? And should the, proof roll also take into account what the actual in-situ strength is based on DCP testing or other forms of testing? So, obviously we'll look at alternatives later, but at this stage we're still looking at what the subgrade strength needs to be, because we obviously failed it at, a stiff clay. So it must be higher than a stiff clay, right, to pass most subjective visual testing. So just coming back to Ostrodes, this chart is in Ostrodes Part 2, Guide to Pavement Design. You can see that generally, DCP blows of about 3 would equate to about penetration of 30 millimeters per blow, which is roughly about a CBR of about 6 to 8. So high CBR, we shouldn't have been getting any visible deflection, and yet we ended up having to rip half a meter of the road out, subgrade out. Again, coming back to this table from DAS, CBR strength of 4 to 8, shear strength of 48 to 96, DCP blows of 2 to 4, which we were getting. So if we're still failing a visual test for a stiff clay, what is that? I guess, what is that point where, what is that deflection? What is that strength, that would, satisfy a visual assessment? So how did we do this model? We did it in Plaxis 2D, finite element model. We only modeled a 1.5 meter thick homogeneous ground, so just clay. We assigned it undrained shear strength, no groundwater, no fire angle, it's undrained, so it's short-term conditions. And the vehicles that we modeled were the smooth drum roller, 12-ton and 7-ton, Bomag manufacturer, so we got their specifications and just used those, and 20-ton and 12-ton water truck, and we got the Isuzu water truck, Isuzu truck, and we looked at tires that those manufacturers use. One of the really important things for this model was actually the contact stress of the smooth drum roller. Now, we know what the width of the roller is, but the actual contact stress varies on the actual strength of the clay itself. Like it'll sort of indent into the clay based on the strength of the clay itself. So you're actually giving it one parameter, which is governed by another parameter which you're trying to determine in the first place. So it's very much an iterative process. So in the paper by Hambledon and Drescher, they talk about, they do talk in depth about this unknown, which is, the indentation of the wheel, and very much being dependent on the strength of the clay itself, and it's a function of the indentation and the contact stress. So but using the equations developed by Hambledon and Drescher, they're not really developed by Hambledon and Drescher, I guess it's just basic mathematics, but they talk about it quite a bit, and we have this equation. The contact length h is 2 times square root of ds minus s squared, where d is the diameter and s is the indentation in the ground. So based on, and we know that the indentation will vary for stiff to very stiff to hard clay. So we assign different indentations to work out what the contact areas are. In the first instance, we adopt a value of 2 for, say, stiff clay, because stiff to very stiff clay, because that's where we think so far it's passing 2 millimeters. We're getting 2 millimeters of deformation where we think it's stiff to very stiff clay. 4 for, say, firm to stiff, and 6 for anything less than firm. And we're getting 100, 150, and 200 millimeters as the H value. Roughly, I've rounded it up to the nearest 10 here. It's usually around 89 or 94 or something. And so we have taken some liberty with the rounding up, but close enough. So we did some modeling. This is just a typical output from Plaxis, just showing some different, outputs. I'm not going to go into too much detail here, but as you can see, like single homogeneous ground model, high stresses at the top, obviously, right underneath the load, lower stresses down the bottom. One of the things that we had to do was Plaxis 2D can't actually model circular loads for it. So we had to do square loads. Sorry, square, not circular. So we have to convert all our circular loads into square loads and contact areas. Outcomes, very high deformations, much higher than I thought. You can see, for 20, we didn't even bother running it, because we started running it around 100, and just to, have some ideas with how many cases we needed to run. And 20 and 30 and 40, firstly, different results. Different results for the smooth drum roller versus the water truck. Very different results. Almost 4 to 5 times higher for the roller compared to the water truck, which straight away told us that the deformation that we were using and the contact area we were using for the smooth drum roller was very conservative. It is, in fact, the deformation is much higher because the contact area has to be much higher. But one of the first things we realized from this test, or from this outcome, was that even undrained conditions in Plaxis are much longer lasting than we thought. Or the indefinite period of time is a big play here in a 2D model. It's just that the proof roll test lasts a second to 2 seconds. Plaxis 2D is still modeling this for weeks, not years, because it's not modeling drained conditions, but it's still modeling an undrained condition where a load is basically sitting on it for an indefinite period of time. So we didn't actually get anything under 2 millimeters at D0, which is directly under the load. It's 2.28, 3.3, and that's for very hard clay, almost weathered rock. So yeah, very high deformation, deflection, much higher than we thought prior to starting, and definitely a result of the fact that the load is indefinitely placed on that ground. It's not there for 1 or 2 seconds, which is what a proof roll test is. Just some graphical outputs, as you can see. Yeah, very high loading, even at very high shear strength. Just more zoomed in look at the output. Like I said, very high deformation at very high loads even. Plaxis 2D is modeling much longer loading than an instantaneous load applied by a proof roll. Obviously, let's rerun the model again with larger deformation leading to a larger contact area for the smooth drum roller. And also let's model the water truck with 700 kPa. So rather than using the actual tire width and the actual tire load, let's just make it whatever size it needs to be 700 kPa. Because when we were actually modeling it for the 280 millimeter width that the tire actually was, we were actually getting a load of about 350 kPa. So we reduced the contact area for the tire, so we would get 700 kPa, which would actually lead to higher deformation. But on the other hand, we reduced the outcome for the roller by increasing the indentation, therefore increasing the contact area, therefore reducing the load, which would ultimately lead to a reduced deformation. So we are somewhat guiding the result, but it's an iterative process, because we are, this is more trial and error at this stage. So again, we looked at a paper by Hambledon and Drescher where they actually looked at, what the deformation typically would be under a smooth drum roller, not a smooth drum roller, the kind of roller they use back in the US of A. So they did a field trial. They got up to 100 millimeters of rutting on material which was basically stiff to very stiff clay based on those DCP values. So I was surprised by that. The rutting was so much for stiff to very stiff clay. And we talk about visible rutting of 2 millimeters, and this is getting up to 90 millimeters. So this is the kind of roller they used, very different from the one we use in Australia. And you can see, very high rutting. Yep. So anyway, we doubled the allowable rut depth, leading to increased contact area, therefore, which would ultimately lead to, lower deflections, deformations from the plexus model. The paper by Colin, Brander and Smith, which is an Australian paper, said that as you reduce or increase tire pressure, and you're obviously going to have a correlated increase or reduction in deflection. So I wouldn't say it's a one-to-one, but it's close enough. So we can see that our deformations for the roller, once we've sort of doubled the contact area, they're actually more than halved. And for the water truck, once we go from a 280 diameter tire contact area to a 190 mil circular diameter, they more than doubled. So the tire pressure more than, the deformations from the tire more than doubled, and we hadn't quite doubled the load. And for the roller, they more than halved when we doubled the contact area. So now they're more close to each other, and I think that might be a more realistic assessment. Trial and error. Some graphical outputs. Let's do another case. Let's model it for a reduced loading, see how that goes. Choose a smaller roller, smaller water truck. Interestingly, using a smaller water truck doesn't actually lead to reduced loading, because it's all dependent on an axle configuration. If we go from a tandem axle dual tire to a single axle dual tire, you actually increase loading. So not always the best outcome, or the lowest loading. So as we can see, a single axle dual tire go up to 10 tons, 2.5 tons per tire, whereas a tandem axle dual tire you go to 16, and it's actually 2 tons per tire. So the other limitation of the Plexus 2D model, it's 2D, it's not 3D, so we couldn't actually model 2 axles side by side. So that was a limitation of the model as well. Some of the outcomes from that, smaller loading, smaller deformations for the roller as expected, but the water truck higher than previously, so as expected, higher loads. So graphical outputs, discussions. So why the high deflections? Obviously, because we're not modeling instantaneous loading, which is what actually happens in a proof roll. We're actually modeling undrained strength parameters for the clay, but an indefinite period of time. So at this stage, there's a lot of unknowns still. This paper actually created more questions than it answered. Yep. The time of loading, Colin, Brander, and Smith, Mangan, Brown, all basically concluded that the time of loading is very important, and the paper basically, the Plaxis 2D model, proved that again. The time of loading is very important. Like, we need to define the time of loading, for each pass, or how many passes, or what speed the vehicle should be driven at, and what, that time of loading should be. And should it be rigid or pneumatic? Now, I'm not going to go into too much detail about this one because different papers conclude different things, and I think this is largely dependent on personal experience, maybe from each of these papers. So, yep. Limitations: 2D model in Plaxis, so we couldn't model the dual axles properly. Software unable to model instantaneous loading, so we need to find another software that can do that. Plaxis 2D wasn't able to do that. How do you model instantaneous loading? Like, again, time of loading. What is that time? 1 second, 2 seconds, 5 seconds? How many passes? Homogeneous soil model, obviously soil is not homogeneous. Just a DCP test from 1 meter apart can get different numbers. No groundwater in the model. Yep, groundwater always plays a role. And contact area with a smooth drum roller. It's an iterative process. One leads to the other, which makes you go back to the first point, and you keep it reiterating. So, iterative model. Alternatives: lightweight deflectometer testing. Are we measuring modulus, or are we measuring uniformity? What are we measuring? Maybe we say we do a modulus test to make sure the subgrade meets the modulus requirements, and then we do a proof roll test afterwards just to identify soft spots. And if it meets the modulus requirements, you only rip out the soft spots, not the entire 300 meter length of road, right? Intelligent compaction, another good alternative. It'll look at the soft spots and confirm compaction. So, conclusions and recommendations. The Plaxis 2D model proved more than anything that time of loading is very important. Number of passes, time of loading is very important. Some unknowns, such as the contact area for a roller, contact area for anything really, it's a bit of an unknown at this point. Even a tire, we model it as a circular plate and a square plate at times, but how do we really know? And the accuracy of the model. Plaxis finite element, sure, but we should always compare models with real life situations. One of the other outcomes, it's obviously not the weight of the vehicle, it's more the actual configuration for a truck. You could have something that might be 50 tons, but if there's multiple axles with multiple tires, then the load per tire is actually less. Some of these trucks that transport turbines to wind farm sites actually have very low tire loading, because they have so many tires, whereas a garbage truck has very high tire loading because it has few tires. So at this stage, we weren't actually able to answer the question that we started off with, which is subgrade strength required to pass a proof roll, because the model had limitations. But one thing we definitely concluded on was that the time of loading matters significantly. Contact area is very important and somewhat unknown. And subgrade modulus is very different from subgrade uniformity. And does a proof roll test need to measure subgrade modulus, or does it need to measure subgrade uniformity? And if the subgrade modulus is known and is sufficient, this proof roll test should only be used to rip out soft spots or identify soft spots. Yep. Awesome. Thank you for listening, and I hope you enjoyed it.